Hello everyone. We are going to talk about graph algorithms. This is the very first video on the series of topics that we covered over graph algorithms, and we will start with BERT first search. But why we care about the graph algorithms? Many problems in computer science can be modeled in a form of a graph as a graph problem. For example, in social media, the people are going to be, modeled as nodes, and their relationship between each other. That, for example, David is friend with Jack. These kind of relationships can be considered as edges, or the whole World Wide Web. Different pages are going to be the nodes, and the hyperlinks between them is going to be the edges. Or for example, in applications like the Google Map or any application that finds the path, you can think of street intersections as the nodes, and the highways, the streets between them, as the edges, and you wanted to actually find a path, for example, from one node to another node, from one point to another point. The computers network, the whole network can become considered as a graph. Different computers are going to be different nodes, and the fiber optic cables between them that actually create some connection between them is going to be the edges. Many different problems can be mapped, can be modeled using a graph problem, using a graph. So I'm going to first define what we called undirected graph, and later on we will see the definition of directed graph. So we show an undirected graph usually as G, and which is a pair of a set of nodes V or vertices and a set of edges that we call it E. So V is going to be the set of nodes, vertices, and E is going to be the set of edges. Usually the time complexity of the algorithms that we discuss over the graph, not usually, always, the time complexity will depend on the number of vertices, the number of nodes, and the number of edges. So sometimes you will see that instead of actually showing the number of vertices, because you can see that V is a set of nodes, E is a set of edges, so the size of E, the number of nodes, usually is referred as N, the size of edges is referred as M. So in different textbook, in different notation, either they use N and M as the number of vertices and edges, or just simply show it as the size of the, using this pipe character, the size of V or the size of E. So nodes, you can actually see the nodes here, and the number of, for example, node 1, and then edges are going to be some connection between these nodes. So here we can actually see an undirected graph. We call it an undirected graph because when you see there is a connection from 1 to 3, there is also a connection from 3 to 1. So if you can go from 1 to 3, or you can go from 3 to 1. So all the edges are undirected, or you can actually think of it as bidirectional. You can go from this way or that way. So how we show a concept like a graph in computer? Anything that we work on in computer, we have to represent it, store it in memory. So we need a kind of data structure. There are two different regular ways to show a graph. The first one is adjacency matrix, which is going to be a two-dimensional array or n by n matrix, that each row and each column show one node, and the entries, for example, an entry like at row U and column V, the value of the entry, because it is undirected, we will actually represent it as, this is undirected and unweighted, we will represent it as 1, which means that there is a connection from U to V. And because this is undirected, definitely if the direction, the entry of AUV is equal to 1, because this is undirected, VU is also going to be 1. If there is no connection between U and V, the entry of row U and column V is going to be 0. So what is the space complexity of this data structure? It's clear that the space complexity is going to be n square, where n is the number of vertices. It takes too much space, and you see that if your graph is undirected, you are using you are storing the edges twice. But the good thing about this representation is that accessing to each edge is going to be constant. If you wanted to see that if there is an edge from U to V, you simply just refer to the entry UV in the in your array, and the access is constant. Accessing to any entry in any cell in your array is going to be constant, and you can access to that in constant time. So this is the good thing about that, and the bad thing is it takes too much space, especially if your graph is sparse, if the number of edges is very low, so you are wasting too much space. That's why there is another way to represent a graph. This is called the adjacency list, where we have n different linked list, and each link for corresponding to each edge. And in each linked list, you for example, the linked list for the node 1, you will keep all the nodes that you have access to. So for example, for 1, you only have the 2 neighbors, right? 2 and 3. There's a connection from 1 to 2 and 1 to 3. So in the linked list for 1, you only actually have 2 nodes. That shows the nodes 2 and 3. For example, the node 2, there are 4 different connections, right? So I have stored 1, 3, 4, and 5. So the good thing about this representation is that you just take as much as a space as you need. So if you have m edges, in total you are going to keep 2 multiplied by m nodes in all of your linked list. Okay, this is not going to be depending on n power 2. It just depends on m, and if your graph is a sparse, linked list or adjacency list is going to be a better representation, because it takes much less space. But the bad thing about this one is that if you wanted to check the if you wanted to check if there is a connection from one node to another node, you have to search in the linked list. For example, you wanted to see that if there is a connection from node 2 to 4, you have to look at, you have to start from the beginning of the linked list corresponding to the node 2, check all the nodes until you find the vertices that you are looking for. For example, here we are looking for 4. Okay, so the time complexity of checking each edge is going to depend on the length of the linked list, where the length of each linked list is going to be the degree of that node. So here let me actually define this notion as well that we define a degree of a node to be the number of edges that we have for that node. So for example, the degree of 2 is 4, the degree of 1 is 2, the degree of 7 is 2, and so on. So yeah, that's it. So we have two representation, adjacency matrix and adjacency list. Depending on the size of the graph, the shape of the graph that you have, you may either go to, and if the space complexity is important, more important for you, or time complexity, you either choose the adjacency list or the adjacency matrix. So let me actually define a couple of more notation that we refer to them in graph algorithms a lot. The first definition is path. We will define a path in an undirected graph G to be a sequence of k nodes, v1, v2 to vk, with this property that we know there is an edge between every pair vi to vi plus 1. Okay, so for example, this is a, let me use a different color here. So 1, 3, 7, 8 is going to be a path, which actually shows that from 1 to you go to 3, you go to 7, then you go to 8. What is the length of the path? If you have k nodes in your path, the length of the path is going to be k minus 1. The length of the path is going to be the number of edges between all of these nodes that you are passing. We will usually call a path as we only call the simple paths as a path, because you can see that you can have a path that has some cycle in it. But when we actually call a path, we usually look for a simple path. So what is a simple path? In a simple path, none of the nodes are going to be repeated. So in your sequence, all of the nodes should be distinct nodes, and it means that there is no cycle in your path. So if you have a path that the first and the last node are the same, you would create a cycle. For example, 1, 3, 2, 1 is a cycle. It actually represents, you start from 1, go to 3, go to 2, and then you come back to 1. So this is a cycle. Another definition is about the connectivity in the graphs. So we would say that two nodes in an undirected graph are connected if we can find a path from u to v. Because this is actually connected, you can consider it as a path from u to v or v to u, because if there is a path from u to v, there is also a path from v to u. So based on that, we would say a graph, we call a graph to be a connected graph if all the pairs of nodes in the graph are connected from, there is a path between all of them. If you start from one node, you can visit all the other nodes. And if the graph is not connected, so it means that you have actually more than one set of nodes that they are maximally connected. We define another notation for this. So every component, every connected component in a graph is going to be the set of a set of nodes, a subset of nodes that maximally connected, which means that, okay, so 1, 2, 3 is not a connected component. If you can actually expand it and cover 7, 8, 5, 6, and 4. So connected component is going to be a subset, a maximally connected set of nodes that all of them are connected to each other. So here in this graph, we have 3 connected components. So when you have a graph, in many cases, almost every in any algorithm that you run over the graph, you're going to visit a couple of nodes in the graph. If you wanted to visit all the nodes in graph, this is going to be called graph traversal. If you remember from COMP359 that we covered the different, we mainly focused on three structures in COMP359. So, and we had different tree traversal that visited all the nodes. Tree is a form of a graph. In fact, graph is a more general form. So if we want to visit all the nodes in the graph, the algorithm is going to be called graph traversal. And in general, we have two different graph traversal. One of them is called breadth first and the other one depth first. In this video, I'm going to talk about the breadth first algorithm, and we will see many applications for breadth first. So some of the problems that we can solve using a breadth first algorithm, I have actually listed them here to show you that how interesting this algorithm can be. For example, assume you have a graph, you wanted to see that if it is connected or not. You can run a breadth first algorithm over that to check if the graph is connected, all the nodes are accessible from each other. If or you have a graph, you want to find all the connected components. If the graph is not fully connected, you want to find all the connected components. Again, using breadth first search, you can solve this problem. You have a graph and you want to check if there is a path from one node to another node. You can run a breadth first search and it gives you not only the path, it actually can find you the shortest path between two nodes. So breadth first search has a lot of applications. So what is the breadth first search algorithm? The whole idea of the breadth first search algorithm is that you started from a node and you wanted to visit all the other nodes, and you visit the rest of the nodes level by level based on the distance to the original node, the first node that you started at. So here, assume you wanted to start from node 1. Okay, so you visit node 1, and for you, node 1 is going to be at level 0. Then you visit all the nodes which are directly connected to 1. And this actually makes sense. If you are at 1, you can only visit the nodes which are the neighbors of this node, right? So you visit 2 and 3. So in the next level, because you can actually visit 2 and 3, from 2 and 3 you can visit all the nodes which are directly connected to these two nodes. So for 2 you will visit 4 and 5, and if you are also connected to 3, but because you have visited 3, so you don't count 3 for this level anymore. 3 has already been visited. Then so for 2, this is going to actually cover 2, 4 and 5, and 3 has connection to 2, 1, 5, 8 and 7. So we don't actually cover the connection to 1 has been visited, 2 has been visited, 5 has been visited. So you consider the connection between 8 and 7. So 8 and 7 will be also visited in level 2. And then you actually wanted to visit all the nodes which are directly connected to the nodes at level 2. For 4, you only have connection to 2 and 5. They have been visited, so I don't want to visit them again. 5 has a connection to 4, 2, 3, and 6. 2, 3, and 4 has been visited, so you will add another connection from 5 to 6. So 6 also will be visited at the third layer or at the third level. 8 doesn't have any connection except 3, which has been visited. 7 has a connection to 3, and in fact also it has a connection to 8. But because it has been 8 has been visited, so we can just ignore that. So we are done, because after that, if you look at 6, 6 only has one connection, the node 5 that has been visited before, so we are done, we are going to stop. But how can we implement this algorithm? We can implement it using a queue. The whole algorithm is that we are given a graph and a node that's going to be the starting point where you should start your BERT first search. Let's call it S. I need a queue because the queue actually helps me to take care of all the nodes in each level and make sure that when you are visiting the nodes, you visit the nodes in the order that you pushed the values, you enqueue the nodes into the queue. Okay, so if I wanted to run this algorithm, to actually cover it, let me run the algorithm over this example. You start from node S and you create a queue, an empty queue, and you push the value then node S into the queue. You remember that when I have actually discussed about these nodes, when, for example, after 1 you visit 2 and 3, right? When I am visiting 2, because 2 also has a connection to 1, you don't want to visit 1 again, right? So I have to store this information somewhere. That's why I'm using some additional array, Boolean array, let's just call it visited, and we initialize all of the size of the array is equal to the number of nodes, and we initialize all of the nodes to be the visited for all of the nodes is going to be false. You haven't visited anything, right? Then you start from node S, you enqueue S to your queue, you put S to your queue, and so you visit the node S, right? So we mark the visited S to be true. Then the only thing that we need to do is just traverse over the queue. Each time just remove one node from the queue and visit all the connections, all the neighbors of this node V if they haven't been visited before. Okay, so the whole thing is that you just remove something from the data structure, the queue structure that you have, and you visit all the neighbors of you, all the neighbors of you. If it hasn't been visited, you push it to the queue because later on you want to visit the neighbors of that node. And you also, because you have, whenever you push them to the queue, it's just like you visit them. So we have to mark them as visited as well. So we store true in the array V. So let's just call this algorithm over the example that we had. You start from the node 1. Let me use a different color. You start from the node 1. So it's just like you visit this one. I'm going to put a circle around all the nodes that has been visited. You push it to the queue. Then in your loop, here, you start removing one node from the queue and push all its neighbors which hasn't been visited to the queue. So 1 will be removed from the queue. So you have 1, you actually check all the neighbors of 1. 1 has a connection to 2 and a connection to 3. So for 2, you check, is 2, has 2 been visited? No, this is actually false. So you push it to the stack, to the queue, and you marked it as visited. The next neighbor of 1 is 3. Has 3 been visited? No. So you push it to the queue and then marked it as visited. Now if you actually go back to this while loop, you will see that the queue hasn't been empty. The queue is not empty, so I have to actually remove another value from the queue. So the next node that will be visited will be 2. 2 will be removed from the queue. Okay, so all the neighbors of 2, we need to actually check them. The first neighbor is 1. Is 1 visited? Yes. So I'm not going to push it back to the queue. If you push it back to the queue, you will see that you will be in an infinite loop, right? So 1 will actually push 2, 2 will push 1, and so you will actually stuck in a loop. So I don't want to visit 1 anymore. I have visited that. The next node is 3. 3 has been visited, so I'm not going to push 3 to the queue again. The next node is 4. 4 hasn't been visited, so you will push it to the queue and you marked it as visited. The next node is 5. 5 hasn't been visited, so you push it to the queue and you marked it as visited. So 2, 4 and 5 has been visited now. So you are done. You go back to the top of the loop. Queue hasn't been empty yet, so you pop another value from the queue. So this time it's going to be 3. Now you see that queue helps us to make sure after you are done checking 2, the next node that you will check and visit its neighbor is going to be 3, not 4 or 5. 3 has been pushed to the queue, has been enqueued before 4 and 5, and that's why it's give me this nice connection that you visit the nodes level by level. This is exactly the property that I need to find the shortest path. From 1, the 2 nodes which are directly connected are 2 and 3, so they are going to be at distance 1. So you visit all those nodes at distance 1 from 1. Then you visit all the nodes which are at distance 2. So after 2, the value that will be visited, the node that will be visited is going to be 3, not 4 or 5. This is the property of the queue that helped me to visit the nodes level by level. So for 3, I have 5 different connections, 1, 2, 5, 7, and 8. 1 has been visited, so just let it go. 2 has been visited, 5 has been visited, but 7 hasn't been visited, so you can push it to the stack, to the queue, and you marked it as visited. And also 8 hasn't been visited, so you put it in the queue and you marked it as visited. Okay, so if you go back to the loop, you will see that the queue isn't empty, so I have to check the next value, remove the next value from the queue and check it. The next node is going to be 4. 4 will be popped from the queue. 4 has 2 connections, 2 and 5. Both of them has been visited, so you don't push anything to the queue. So for 4, we don't have any new nodes being pushed to the queue. The next value that will be popped from the queue is going to be 5. We dequeue that, we remove it from the queue. So for 5, I have 4 different connections, 2 is visited, 4 is visited, 3 is visited, but 6 hasn't been visited. So you push it to the queue. It will be pushed to the end of the queue, and you marked it as visited. Then you are done with 5. The next node that will be visited, will be removed from the queue is 7. You pop it from the queue. 7 has 2 connections, 3 and 8. Both of them are visited, so you don't actually push anything to the queue. The next value that will be popped from the queue is going to be 8. 8 has 2 connections, 3 and 7. Both of them are visited, so nothing will be pushed to the queue. The next value that will be removed from the queue is going to be 6. Actually remove that. And the queue will be empty. 6 only has 1 connection, 5. It has been visited, so you don't push anything to the queue. Then you will see that the queue will be empty. The whole algorithm will stop. And we visited the nodes layer by layer. So what is the time complexity of this algorithm? You can see that all the nodes has been pushed to the queue once, not more than once. So it actually tells me that how many nodes will be removed from the queue. So I have V number of nodes, N number of nodes, all of them will be pushed to the queue. And in each iteration of the main loop, I am going to remove 1 node. So there is the number of loops that you have, the number of iterations that you have in this outer loop. In the while loop, it's going to be n, the number of iteration of this. Probably I should actually just show it this way. The number of iteration is going to be n. So the number of iteration here is going to be n. But I have another loop inside that. There is a nested loop here. How can I calculate the total time complexity, the total number of time that this part is going to be done? You can see that, pushing, pushing to the queue is going to be constant, removing from the queue is going to be constant. So whatever you have here is going to be a constant cost. So the cost here is going to be constant, right? In total, I just need to know that how many times this loop, the nested loop, will iterate in total. If you get the summation of all the number of iteration of the outer loop and the inner loop, you will need to just know that how many times this part will be executed. And basically, I don't have a clean pattern for this one that just tell you that how many times the nested loop is going to be iterated and multiplied by n, because this is going to be depending on the number of neighbors of each node. Some of the nodes might have just 1 neighbor, some of them might have n minus 1 neighbors, right? They might be connected to all other nodes, or they might be connected to just one another node. But I can calculate how many times in total they are going to be calculated. They are going to be, this inner part is going to be executed. It will depend on the number of edges in total that I have, because the outer loop will iterate over the nodes, the inner loop will iterate over the connections of each node. So it nicely just gives me this idea that for each edge, you will check this if statement twice. For each edge, for example, if you have an edge from U to, there is an edge between U and V. Once for U, you will check V as a neighbor, and once for V, you will check U as a neighbor. right? So in total, this is going to be this part, this if statement will be executed 2 multiplied by the number of edges. So in total, this is going to be executed O of M, where M is the number of edges. Usually, because we don't know how many edges we have, maybe the number of edges is going to be smaller than the number of nodes. Maybe for some of the nodes you don't have any connection. Usually we show the time complexity when it just depends on M. You usually just write it as M plus N, because it definitely depends on N as well. It just shows you that if the size of M is not clear, usually the number of edges is going to be greater than the number of nodes, but sometimes it might be smaller, right? So if the graph is very sparse. So we usually actually just cover it as N plus M to just make sure that you cover the full outer loop as well. So the time complexity of your BERT first search algorithm is going to be O of N plus M, the number of edges plus the number of nodes. So there are very nice properties about the BERT first search algorithm. You can say that after you run the BFS, this array visited is going to tell me something. If there is a connection between S and any node, all those nodes are going to be marked as visited. We can prove that if there is a connection between S and any node V, those nodes, after you run the BFS starting from S, those nodes are going to be, the visited for them is going to be true. You will visit them. If there is a connection, if there is a path from S to any node, the node will be visited. So I am going to actually leave the complete proof here for you to study. I have written the full proof in the lectures, but the idea of the proof is that if you start from any node, you will visit, this is very intuitive. You started from node 1 in this example, you visit all the nodes which are directly connected to that node. Okay, and from those nodes, you expand it. You will visit all the nodes which are connected to that. And you basically just grow, and it is just like you are growing and you are distributing this it's just like you are actually putting a flow starting from node 1, and from node 1 it actually reaches to 2 and 3. From 2 and 3 it reaches to all the nodes which are connected to them. And so whenever you put a node in the queue, you also marked it as a visited, right? So it is very intuitive that if there is any path from S to any of the nodes, those nodes will be visited at the end, will be pushed to the stack, and you actually mark them as visited. So let's see a couple of problems that those problems that we have talked about at the beginning, that we can solve them using a BFS. Assume we have a graph and we have 2 vertices S and T. We want to see if there is a path connecting S to T. How to solve this problem? We wanted to actually see that if there is a path from S to T, you can just start running a BFS from starting from S, and if at the end T is visited, it means that yes, there is a path from S to T. And this is directly comes from the theorem that I have just discussed here, that if there is a path from S to any node, all the nodes will be visited. And if any node is visited, it means that there is a path from S to V. This is an if and only if statement. So the algorithm is just run the BFS over the graph starting from node S after the BFS if visited T is true. The answer is yes. If it is false, it means that there is no path from S to T. Another problem is that assume we have a graph and a vertex, a node S. We want to find a connected component that contains S. If you think about it, the algorithm is very simple. You just need to run the BFS from S, and it finds all the nodes which can be connected, which can be reached from S. Okay, but we have to also show that all those nodes can be there is a connection from them to S as well. The algorithm is very simple because the graph is undirected. If there is a path from S to any of those nodes, there is also a path from those nodes to S. Okay, so you just run the BFS, and all the nodes which are visited, the visited for them is true, they are going to be a part of the connected component. So you will find them connected component containing S. Let me show you an interesting example of finding a connected component in a graph. Just think about any painting application that, for example, some picture like this, that you wanted to change the color of the whole, this green blob to another color like blue. The application works in this way that if you click on any pixel and then change the color, all of the other pixels in the same blob will be changed to the new color. But how we find those pixels? So you can actually model it using a graph and just show that these pixels, which are these neighboring pixels, if they are in the same bulb, if there is a connection between them, it means that if the color of all of them are green, so it means that there is a connection between them. If the color is black, so there is no connection between the green one and a black one. So in this way, you can model this using a graph, and we try to actually find a connected component. Starting from where you clicked, from that pixel, just find all the other pixels, neighboring pixels, which are connected. They have the same color green. This is exactly the problem of finding a connected component. Another problem, assume you have a graph. We wanted to find all the connected component in the graph. So how we can solve this? The algorithm is that you might have one connected component or more than one in your graph. You don't know even if the graph is connected or not. What we can do is we can start from one node because we wanted to find all the connected components. It doesn't matter which node you start with. You can start from one node, run a BFS over the graph starting from this node S, and it actually marked all of the nodes which are connected to S, which are accessible from S, right? It gives you a connected component. All those nodes will be removed from the whole set of nodes. If it actually just removed, if you covered all the nodes, if you have visited all the nodes, there is only one connected component and all those nodes will be in C. So if you remove all of them from V will be empty and the algorithm will stop. But if some nodes remains that hasn't been visited, it means that you have more than one connected component, right? So again, you take another node from V, you see that all those nodes that have been visited in the first connected component have been removed, so you don't choose them again. You choose another node, again run the BFS, it finds all the nodes which are connected to this node, it finds another connected component, they are going to be, all of them will be marked, remove them from V and just repeat. So there is going to be a loop until you covered all the nodes, until you find all the connected components. So what is going to be the time complexity of this algorithm? Because you see that we are running a couple of BFS if you have more than one connected component. Like if you have a graph like this, doesn't really look good. You will run BFS once over, for example, you call it over this one, it will you will run BFS on this part, then you will run BFS over this one, then you will run BFS, for example, over one of the nodes here. So you will run 3 BFS. But does this actually affect the time complexity in total? The thing is, for each of these components that you run the BFS, the time complexity will depend on the nodes which are in this connected component and the number of edges here, not all of them. So the time complexity that would take to run the BFS over each component will depend on the number of edges here and the number of nodes here. So this is going to be all just cover. How can I show that? So let's just show it as V1, which is the subset of V, that all the nodes here plus E1. The time complexity that you run the BFS here, it's going to just depend on the number of nodes that you visit here and the number of edges that you visit here. So V2 plus E2, and here V3 plus E3, where V is going to be the set of the union of V1, V2, and V3, and E is going to be the union of E1, E2, and E3. So in total, the time complexity is going to be the summation of the time complexity here, here, and here. So again, this is going to, you can actually just write it as n plus m, or just the size of the number of edges, the number of nodes, and the number of edges. So this is going to be the total time complexity, which is equal to the time complexity of a full BFS if the graph was connected. So another, for some of the problems that we are going to solve, we need some more definitions here that depends on the BFS. So when we run the BFS over the graph, it will in fact give us a tree. So if I go back and show you the original example that we run the BFS, if you look at this, the nodes and the edges that I marked, for example, from 1 you visit 2 and 3, from 2 you visit 4 and 5, from 3 you visit 8 and 7, from 5 you visit 6. So you will see that I'm not checking all the edges here, only a subset of edges. This is going to give me a tree. And this tree is going to help me to actually solve and prove many different problems and theorems. Okay, so the first theorem here is about, in fact, the tree. So because I'm going to talk about the trees, let me just give you a small definition of a tree and some specific properties over the tree that are very interesting and helps us to do, to solve problems and or prove some problems, some theorems. So what is a tree? An undirected graph is called a tree if it is connected, all the nodes are connected to each other, and there is no cycle in that graph. Okay, so this is the formal definition of the a tree. So we call an undirected graph to be a tree if all the nodes are connected and there is no cycle in that. From this definition, we can prove three different specifications for a tree, which if two of them is true, you can say that you can immediately actually prove the third one. For example, if you know that a graph is connected and if you know that the graph doesn't have a cycle, you can prove that the number of edges in the graph is going to be n-1 when n is the number of vertices. So the number of edges is going to be number of vertices minus 1. If you know that your graph doesn't have a cycle and the number of edges is n-1, you can prove that the graph is connected. If you know that the number of edges is n-1 and the graph is connected, you can prove that there is no cycle. So you have a tree. So a tree will actually just look like this, right? A general tree in graph theorem. If I take any of the nodes and ordered the rest of the nodes just based on the distance from this node, I would get a hierarchy, something like this. If, for example, if I take 1 and just order the nodes based on their distance from the node 1, you will see that, okay, so 2, 5, and 7 will be actually at the next level. So the first level is going to be the node 1. All the nodes which are connected to 1 directly is going to be at the next level, and then the rest of the nodes which are connected to these are going to be at the next level, and so on. So it gives you a form of a hierarchical structure, right? We call this a rooted tree, that we considered one node as a root in your tree, and the rest of the nodes have been ordered just based on the distance from the node that you considered as a root. This is going to be a rooted tree. So this is a general tree. If you take any of the nodes, you can create a rooted tree based on this fact that, okay, that is whatever is going to be your root. So now I'm going to actually go back and talk about the BFS algorithm that we run, and the way that we visited the nodes and the edges. If we look at the BFS algorithm, if you start from, for example, the node 1, the result is going to be a rooted tree, that the node that you start is going to be the root of that tree. You will cover all the nodes which are connected, and you will cover only a subset of edges, so the result is going to be a tree. So for example, in this case, you will first visit node 1, then you visit node 2 and 3, right? So this is going to be the tree that's going to be the result over your graph. You had a general graph, but the output of BFS can be represented as a rooted tree. So from 2 you visit 4, from 2 you visit 5. You see that I'm marking those edges that are a part of this tree as well, those edges that you visit through them. From 2 you visit 4 and 5, so I'm just going to actually cover this edge and this edge. From 3 you wouldn't actually visit 5 or 2 or 1, right? Because they have been visited so far, so I'm not going to add any edge for them. But from 3 you visit 7, so this edge will be covered, and you visit 8, so this edge also is going to be covered, and from 5 you visit 6. So this exactly gives me a rooted tree in this form, that 1 is going to be the root. From 1 you have a connection to 2 and 3. They are going to be at the next level, or you can call it as a layer 1 or level 1. From 2 you have a connection to the node 4 and 5, you see that I'm just following and adding those edges that I have added through the BFS. And from 5 you have an edge to 6 and you visit 6, and we are done. You are covering all the nodes, but you just cover n minus 1 number of edges, and those edges are going to be exactly those edges that you visit a new node that hasn't been visited before. So this is the result of your BFS, which is a rooted tree. We call it a BFS tree. And the nice thing about this tree is that if you start from the root, the node 1, the shortest path to all the nodes from the root, the node 1 in the original graph is available in this BFS tree. The shortest path from 1 to 2 is exactly the this path that you have from 1 to 2 in your tree. You see that if you have a tree, the path from each node to another one is going to be unique. There is no more than one path between every 2 nodes that you have in your tree. If there are more than 2 paths, if there are more than one path, it basically means that you have a cycle and it's not going to be a tree, right? If you have 2 nodes in a tree, U and V, if there is more than one path from U to V, it means that there is a cycle, right? This is one path, and you go from U to V, and you can actually go from V to U on the other path, and this is going to give you a cycle. And this is a contradiction with the definition of a tree. So in a tree, we can prove that there is a unique path between every 2 nodes. And the property that we have over the BFS tree is that the path from the rooted node, from the node that you run the BFS, to every other node is going to be the shortest path from that node to all the nodes in the original tree. So the shortest path from 1 to 7 is going to be this path, which is going to be this path in the original. The shortest path from 1 to 6 is going through 1, 2, 5, and 6. So this is going to be the shortest path from 1 to 6 in the original graph. Although there might be actually more than one shortest path, but it gives you one of them. And this is very nice. If you run the BFS over the graph, over one of the nodes in a graph, it gives you the shortest path from that node to all the other nodes in your graph. So how we can, because in the original BFS algorithm that I showed you, we didn't keep the edges, right? So we need to keep them somewhere. How to create a tree? We can update the previous algorithm, and by just creating one more array, that array is going to keep track of the edges that we covered. And so, to even actually makes it more practical, we don't just directly store the edges. We will add an array that we call it a parent. We call that array parent. And basically for each node, it tells me, for this node, where I reached to this node. Okay, when you are visiting this node, where you reached to this node. For example, the parent for 8 is going to be 3. It's just telling me that you visited 8 through 3. So because the parent of 8 is 3, it basically tells me that I have actually used the edge 3 to 8. Okay, so for every node in your tree, you are going in your graph, you are going to have a p of u is going to be some node v, which basically means that there is an edge from v to u, and that edge is going to be a part of the BFS tree. Okay, so all of these are going to be a part of your BFS tree. So not only you are covering all the edges that you have visited as a part of BFS tree, but also it gives you the complete path. Starting from any node, you can find the shortest path from the original, from the starting point to that node by just reverse following the parents. So how we are going to actually update and keep this information, I'm going to add this variable, this array parent that you just initialize the parent of the starting node to null, because no one is going to be the parent of the starting node, right? So the parent of a starting node is null. The parent of the rest of the node is going to be one of the nodes in the graph. And whenever I am visiting in this if statement, whenever you visit the node v, you are visiting it through u, right? So the parent of the node v is going to be the node u. Okay, you actually put it there. Not only that, I can also update the algorithm to just give me the distance, the shortest path from the node S to every node. So I'm going to add another array, we call it dist, and we initialize all of the nodes to be, the distance of all of the nodes can be actually infinite except the distance of S. That tells me that distance of S to S is 0. Which is actually correct, right? The distance from each node to itself is going to be 0. So you initialize this one as 0. Then as you visit every node, you will update it, the distance of the node to be the distance of its parent plus 1. So basically, if a node hasn't been visited before, so the distance is going to be infinite. Whenever you visit it for the very first time, you are visiting it through through a parent, right? So this is going to be the node u, right? And through node u, there is going to be some distance from the node S, some way you have actually visited u, but you haven't visited the node v before. Right, so the shortest path from S to V is going to be through this path. You reached from S to U, and then you reach from U to V. So what is going to be the distance of V? Whatever is the distance of U from S to U plus 1, because you are actually covering this edge as well. The distance of V is going to be the distance of u plus 1. And you would never actually update this again, because you cannot visit the node v again. This is the first time that you are visiting the node v, and this is going to be the shortest distance from the node S. So these are all the, in fact, theorems that we have about the BFS series, that if you create a tree by using all the edges like the parent v and v, this is going to give you a tree that we call it a BFS tree. We can prove that this is a tree, there is no loop in that, and it is connected. And the other theorem that we can prove is that the distance from node S, the shortest distance from node S to every the shortest distance from node S to every node is going to be computed in dist V. So dist V is going to give me the shortest path from S to every node S. You can prove this one using induction. I have written all the proofs here, but I'm going to skip them because it's going to be too much verbal, and in a video this is going to be too boring. If you had any question, please read the proofs. If you had any question, we can discuss it in the during the office hours. So these are the main two theorems that we had. You get a BFS tree. This is a tree, the set of all the edges, and this gives us the shortest path starting from S. So using these two theorems, we can solve many interesting other problems. And the first one that I'm going to give you is about the bipartite graphs and how we can check if a graph is bipartite. So what is a bipartite graph? We would say that a graph G is bipartite if we can divide the set of vertices, the set of nodes, to two subsets, to two disjoint subsets, so that there is no connection between the nodes in the same set. So all the nodes in V1, there is no connection between them. So if U and V belong to V1, there is no edge like UV doesn't belong to the set of edges. There is no edge between U and V. The only edges that we have is going to have all the edges that you have in your graph. So U should belong to one set and V should belong to the other set. So in this way, we would call it a bipartite graph. And this is an example of a bipartite graph. You see that all the blue ones are going to be one set, all the red ones are going to be another set. And we only have a connection between the nodes in two different sets. So the problem now is you have a graph, you don't know if it is bipartite or not. You want to check that if it is bipartite or no. So for example, if I have a graph like this, is it bipartite? So if you work over this example, you will see that yes, this is bipartite. I can find that these two sets, that for example, if I started from V1, I put all the other nodes which are connected to this one in the other set because they cannot be in this set. So V4, V2, V5, and V7. And from V5, I have a connection to V3 and V6. So definitely V3 and V6 should be in the other set. Right, so from V3, I have a connection to V2, V5, and V7. This doesn't look good. Let me just rewrite it. And V4. So from V6, you have a connection to V2, V5 and V7, right? And basically we covered everything. You covered all the edges and all the vertices. And yes, this is a bipartite graph. But you can see that it was not easy to actually find. So given a graph, we wanted to check if it is bipartite. And the more extended one, if it is bipartite, we want to find the two sets of the vertices, set 1 and set 2, two different set of your bipartite graphs. So here it actually just shows you that yes, this graph is a bipartite graph, and we can rearrange the nodes. This is going to be the set of V1, the set of V2. The problem looks very complicated, But let's start with the facts that we know. If we actually think about any of the nodes in one of the sets, we know that all the neighbors of this node is going to be in the other set, right? So if you start from one of the nodes in the blue set, all the neighbors are going to be on the other set. They are going to be in the red set. All the neighbors of these nodes are going to be on the blue set again. All the neighbors of these nodes at this layer are going to be on the red set, right? This gives me something actually. If you think about running the BFS starting from any of the nodes, it actually gives me this idea that if the graph is bipartite, I will see that all the nodes in the first layer are going to be the nodes in the other set. If you started from a node in the blue set, all the nodes that you visit in your BFS in the first layer are going to be in the red set, and all the nodes that you visit from this, all the neighbors of these ones are going to be again on the blue set. All the neighbors of these ones are going to be on the red set, and so on. You can actually just continue it as much as you have the nodes in your graph. So it exactly gives me the idea that if I run the BFS, it divided the nodes to different sets just based on the layers. So I can think of it as the even layers are going to be in the same set. So whatever you have at layer 0, layer 2, if there are more layers, layer 4, all the even layers are going to be the nodes which are supposed to be in the same set, and all the odd layers are going to be a part of the other set. Okay, so this way, if I take any node, it doesn't matter which node, if you take any node and you run the BFS by just looking at the layers that you visit the nodes, you can just get two different sets. All those nodes that has been visited in the even layers, all those nodes that has been visited in odd layers. And basically this even and odd layers tells me the distance, right? So layer 1 will be all the nodes which are at distance 1. All the nodes in layer 2 are going to be at distance of all these nodes are going to be 2, and distance of all these nodes are going to be 3, and so on. So I just need to run the BFS, calculate the distance for all the nodes. All those nodes which have even distance are going to be in the same set as the node that you have started, and all the nodes which are at odd distance from the starting point are going to be in the other set. This basically just gives me two different sets. If the graph is bipartite, after you get these two different sets, you divide all of the nodes in two different sets. You just need to check if there is any edge between all the nodes in one set. If there is edge, it means that your graph is not bipartite. If there is no edge between them, the graph is bipartite. Not only it gives you the answer of if the graph is bipartite or no, it also actually gives you the two sets. So this is the algorithm. You just run the BFS over, just take one random node, just run the BFS, put all the vertices that has even distance in one set, and all the vertices that has odd distance are going to be on the other set. Then we just need to check the nodes in each of these vertices, each of these sets. All the nodes in set 1, there shouldn't be any edge between them, and all the nodes in set 2, there shouldn't be any edge between them. Here I am assuming that the graph is connected. If the graph is not connected, you can just actually run it over each connected component to see if each of them is bipartite or no. So there's no difference between actually a graph is connected or not. Just expand the algorithm. So what is the time complexity of this algorithm? You can see that the time complexity of BFS is going to be O of n plus m, the number of edges plus the number of vertices. The time complexity of this set, is going to be O of n. You just go over all the nodes and just based on the distance, put it either in set 1 or set 2. And at the last step, I have to check if there is an edge between the nodes in each set. So basically, I'm checking all the edges, right? So the time complexity of this part is going to be O of m as well. So in total, the time complexity of the full algorithm is going to be n plus m. In fact, we need to prove the correctness of the algorithm as well. The proof has two parts. If the algorithm says the graph is bipartite, you have to prove that yes, the graph is definitely bipartite. And if the algorithm tells you the graph is not bipartite, you should prove that definitely the graph is not bipartite. The first part, I think it's quite obvious. Because if the algorithm tells you it is bipartite, it does this sanity check at the end, which makes it quite clear that it gives you two different sets, and you just check that there is no edge between all the nodes in each set, and it is very clear, obvious, intuitive that definitely the graph is bipartite if the algorithm tells you it is bipartite. The other part is that if the graph tells you it is not bipartite, you also have to prove that definitely the graph cannot be bipartite. How to prove that? I have the complete proof, but the whole idea comes from this fact that in the bipartite graphs, we don't have cycles with odd length. Basically, it means that if you actually check any cycle, you started from one node, right, and you come back to this node. So if the graph is bipartite, you go to one of the nodes in the other set. It's not possible to go to any of the nodes in the same set. And from this node, you go back to one of the nodes in the original set, in the first set, right? And from this one, you cannot go to, there is no edge here, right? So if you are looking for a cycle, you have to go back to one of the edges here, then one of the nodes here, and then you come back here. Okay, so it basically tells you that it is clear that in any bipartite graph, we don't have cycles with odd length. You started from any node, you go to the other set, and you come back. So for every going and backing, you have a pair of edges. The number of edges in a cycle should be definitely even. Using this lemma, we can prove that if the graph gives you, if the algorithm tells you the graph is not bipartite, definitely there is a cycle with odd length, and so it means that the graph is not bipartite. So we can just prove that using this lemma. So I'm done with this lecture, which was basically about the BFS and many interesting problems that we can solve using BFS. It covers section 1 and 2 of the chapter 22 from your textbook CLRS, but many of these problems that we discussed here are coming from the textbook KT and DPV. You can also have a look at the corresponding sections in those textbooks.